This metal was once worth more than gold. Today, you might throw it into the recycling bin. Meet aluminum, the lightweight metal behind air, from royal treasure to change the world.
Welcome to The Deep Dive. I'm your host, and today we are looking into the incredible story of element 13, which you probably know better as aluminum.
And I'm your resident tech expert.
Oh.
I am really excited to get into the research for this one because the engineering history here is, well, it's just wild.
It really is. So to kick things off, I want you to picture a royal banquet in the 1850s, right? Under the vaulted ceilings of the Tuileries Palace in Paris.
In the scene, I like it.
Yeah, well, there's a very specific expectation of what wealth looks like at this time. You imagine the most honored guests of Emperor Napoleon III eating off plates made of solid gold or, maybe pure silver.
Right, the historical classics, gold, silver, maybe some platinum if you were like incredibly well connected and wanted to show off.
Exactly. You expect those heavy, shiny metals that have defined human status for millennia. But when you look at the records from Napoleon III's court, that ancient hierarchy is turned completely upside down.
Wait, really? How so?
Well, he routinely hosted dinners where the regular run-of-the-mill nobles were handed the gold cutlery. But his absolute VIP guests, the people he really wanted to impress, they were given utensils made of something far more precious. Aluminum.
Which is, that sounds completely absurd to anyone opening a kitchen drawer today.
Right. The idea that the exact same material we use to, wrap up leftover pizza or toss into a recycling bin was once literally worth more than its weight in gold is jarring.
It's a massive reality check.
It really is. So our mission in this deep dive is to explore the unbelievable journey of this metal. We want to uncover how a material that went from a royal treasure to an everyday essential was unlocked by sheer brute force human innovation.
And we really have to look at the mechanics of that innovation, because without mastering this one specific element, the physical infrastructure of the 20th and 21st centuries just wouldn't exist.
Yeah, commercial aviation, space exploration, the power grid.
Exactly. None of it would exist in its current form.
Okay, let's unpack this, because the early history of aluminum is steeped in a massive contradiction.
Oh, the rarity issue.
Yeah. You read the geological data today, and aluminum is the single most abundant metal in the Earth's crust. It makes up about 8% of the crust by weight. It is practically everywhere. It's literally in the clay in your backyard.
Right. It's the third most abundant element overall, right behind oxygen and silicon.
So the obvious question becomes, if it's the most abundant metal on the planet, why couldn't early scientists just dig it up, melt it down, and forge it like iron or copper?
Well, it wasn't a matter of scarcity. It was a matter of intense chemical stubbornness.
Chemical stubbornness.
Yeah, that's the defining trait of the metal's early history. Unlike gold or silver, which are, relatively inert, you can just find them sitting in a riverbed in their pure form. Aluminum practically never exists in its pure state in nature.
Because it's so reactive, right?
Exactly. It aggressively seeks out other elements to bond with, particularly oxygen. And it forms these incredibly tight, robust chemical bonds that lock the metal away inside complex minerals.
So it was just hiding in plain sight for millennia. People were actually using compounds containing aluminum without knowing it, like alum, which was essential for dyeing fabrics and tanning leather in the ancient world.
Right. They knew the compound was useful, but the metallurgical science to break that oxygen bond, it simply didn't exist yet.
They knew the treasure was inside the chest, but they literally did not have the key.
That's a great way to put it. It wasn't until the early 19th century that chemists even confirmed it was a distinct element waiting to be extracted. The first real breakthrough required a massive chemical workaround.
And this was in 1825, right? With Hans Christian Ørsted.
Yeah, Ørsted, a brilliant Danish physicist and chemist. He managed to isolate a tiny impure sample, but looking at his methodology, he didn't just dig it up. He had to chemically wrestle it away from the other elements.
It sounds exhausting, honestly.
It was. He used this complex multi-step reaction involving anhydrous aluminum chloride and a potassium amalgam. He essentially had to trick the chemical bonds into releasing the aluminum by offering them like a more attractive elemental partner.
Wow. And that reaction was phenomenally difficult, right? Dangerous and incredibly expensive to execute.
Oh, incredibly expensive. Even after Ørsted proved the metal could physically exist in a pure state, scaling that reaction was nearly impossible.
So tying this back to the Napoleon III story, The high cost wasn't because the metal was rare in the ground.
No, not at all. The cost reflected the sheer amount of cutting-edge, 19th century scientific labor required to yield just a few microscopic droplets of this stuff. Owning an aluminum bar proved you had the absolute best chemists in the world on your payroll.
Which is such a flex, but what's crazy is that the intense chemical stubbornness that made it so agonizingly hard for Ørsted to extract is actually the exact same property that makes it so valuable today.
Yes. What's fascinating here is the atomic structure, because it perfectly dictates its real-world behavior.
Let's get into the science of it then.
Okay, so it sits in group 13 of the periodic table, atomic number 13. But the crucial detail is its electron configuration. Specifically, it has 3 valence electrons.
Okay, keeping it simple for us non-chemists, what do those 3 electrons actually do?
Well, those 3 valence electrons mean aluminum is eager to participate in chemical reactions. But they also dictate how the pure metal behaves physically once we finally isolate it. It forms strong metallic bonds in what we call a face-centered cubic crystal lattice.
Right. And in practical terms, that arrangement gives us a silvery-white metal that is incredibly lightweight. The sources say it's roughly a third the density of steel.
Exactly. A third of the weight, yet it remains highly malleable and ductile. You can cold roll it into incredibly thin sheets like aluminum foil, or draw it into miles of wire without fracturing that crystalline structure.
Plus, doesn't that lattice structure make it highly conductive?
It does. The freedom of movement within that metallic lattice makes it an exceptional conductor of both heat and electricity.
Okay, but I have to challenge the durability aspect here. If the metal is so lightweight, so malleable, and as you said, it wants to bond with oxygen aggressively, how does it survive the elements?
What do you mean?
Why doesn't a soda can or, I don't know, an airplane wing just rust away into nothing like an old iron gate out in the rain?
Okay. The comparison to iron is illuminating because they handle atmospheric oxygen in completely opposite ways.
Okay.
When iron is exposed to oxygen and moisture, it forms iron oxide, which we all know as rust. But rust is structurally larger than the iron it replaces. So it expands, flakes off, and exposes fresh, vulnerable iron underneath.
Right, and then that new layer rusts, flakes off, and the cycle continues until the whole thing is just eaten away. It's a progressive structural failure.
Exactly. But unlike rust, which acts like, a flesh-eating disease on the metal, aluminum's oxidation is more like instant scar tissue.
Instant scar tissue.
Yeah. The research shows that the split-second pure aluminum is exposed to the air. Its high reactivity causes it to bond with oxygen. But instead of flaking, it forms a microscopic, impermeable layer of aluminum oxide.
Oh, wow. And the research noted that layer is chemically identical to sapphire, right?
Yes. It is incredibly hard, perfectly continuous, and transparent. It bonds seamlessly to the underlying metal, immediately sealing the wound, so to speak.
So it creates a physical barrier that stops any further oxygen from penetrating the surface. It essentially self-passivates.
Right. Now, it will still react violently with strong acids or bases that can dissolve that oxide layer, but against normal environmental moisture, it protects itself instantly.
That's brilliant. But pure aluminum on its own is still relatively soft, right? Because its atoms slide past each other easily in those neat little rows within the crystal lattice.
Yeah, if you want to build an airplane, you need something much stronger. And this is where alloying comes in.
Right. Looking at the metallurgical data, pure aluminum is rarely used in heavy industry. Instead, engineers mix it with small amounts of copper, magnesium, or zinc.
And the mechanics of that alloying process are fascinating. When you introduce, say, copper or zinc atoms into the molten aluminum, those new atoms are physically different sizes than the aluminum atoms.
It's like throwing a wrench into a sliding set of gears.
That is a highly accurate way to visualize it. In metallurgy, we call it pinning the dislocations.
Pinning the dislocations. Got it.
Yeah, the differently sized copper atoms distort the neat rows of the aluminum lattice. So when physical stress is applied, the rows can no longer slide past each other easily. They lock up.
And that simple addition gives you the lightweight characteristics of aluminum, but the rigid, tensile strength of steel.
Exactly.
Which is exactly what you need to build a modern society. But here's where it gets really interesting, because we are still left with that massive extraction problem.
The bottleneck.
You cannot build a global infrastructure out of a metal that costs a fortune to synthesize in a laboratory. The transition from this ultra-expensive imperial novelty to the backbone of modern industry required completely rethinking how we get it out of the ground.
It required a two-part manufacturing miracle that we still rely on today. And the first step involves sourcing the right raw material.
Which is bauxite.
Right.
Right.
Today, almost all commercial aluminum starts as bauxite. It's this reddish, clay-like rock found primarily in tropical and subtropical regions. It's formed by millions of years of intense weathering.
But looking at the extraction data, raw bauxite is practically useless on its own because it's choked with impurities like iron oxide and silica.
Yeah, you can't just toss it in a blast furnace with some carbon like you would with iron ore. The oxygen is bound too tightly to the aluminum, and the impurities would completely contaminate the melt.
So how did the industry bypass that?
The solution came in the late 19th century with the Bayer process. Instead of just heat, the process uses chemistry and extreme pressure. You take crushed bauxite ore and pressure cook it in these massive steel digesters.
Sounds intense.
It is. They're filled with a highly concentrated scalding solution of sodium hydroxide. The extreme alkalinity dissolves the aluminum-bearing minerals into a liquid solution while completely ignoring the iron oxide and silica.
And those ignored impurities become that notorious byproduct known as red mud, right? Which has its own massive environmental management challenge.
Oh, absolutely. But once you filter out that red mud, you are left with a clear liquid. You let it cool, seed it with crystals, and it precipitates out into a pure, stark white powder called aluminum oxide.
Okay, so you have successfully isolated the aluminum from the rock, but you are still left with the original problem Ørsted faced, right? The aluminum is still locked in that seemingly unbreakable bond with oxygen.
Yep. Exactly. Breaking that bond required the second half of the manufacturing miracle. And this happened in 1886. Two scientists, Charles Martin Hall in the United States and Paul Héroult in France, working completely independently, discovered the exact same process almost simultaneously.
That's always so crazy when that happens in history.
Right. But they both realized that chemical workarounds just weren't powerful enough. They needed brute force. They needed massive amounts of electricity. They figured out that if you dissolve that white alumina powder in a massive vat of molten cryolite, which is a rare mineral that acts as a solvent, you create a liquid bath that conducts electricity.
And then they run a current through it.
Yeah, you lower massive carbon anodes into the bath and pump a staggering electrical current through the liquid.
Okay, so this is the electrolysis phase, the Hall-Héroult process. The electrical current literally rips the oxygen atoms away from the aluminum atoms.
Yes. The oxygen migrates to the carbon anodes, burns off as carbon dioxide, and the pure liquid aluminum metal, being heavier than the solvent, pools at the bottom of the cell where it can be siphoned off.
It sounds like an incredibly violent, high-temperature process. But so what does this all mean? Did this process literally flip a switch overnight for the industry?
Historically speaking, yes, it triggered a nearly overnight revolution in material science. Before the 1880s, aluminum was roughly $1,200 a kilogram in today's money.
$1,200?
Yeah. But after the Hall-Héroult process was commercialized and scaled up right alongside the first generation of large-scale electrical grids, the price plummeted to less than $1 a kilogram within just a few decades.
Wow. Okay, so once that mass production problem was solved, this newly unleashed affordable supermetal became the foundational building block for the entire 20th century. I mean, consider the Wright brothers.
Oh, perfect example.
When they were designing the engine for their very first flight at Kitty Hawk in 1903, a standard cast iron engine block would have been way too heavy to ever get off the ground.
Right, so their mechanic, Charlie Taylor, had to cast a custom four-cylinder engine block out of an early aluminum-copper alloy.
Because the metal's sudden affordability allowed them to hit the critical power-to-weight ratio they needed for powered flight. Aviation was essentially just waiting for aluminum to become cheap enough to use.
And if we connect this to the bigger picture, from there, the alloys completely changed the world. A German metallurgist named Alfred Wilm accidentally discovered age hardening a few years later, which led to the creation of duralumin.
And that specific alloy allowed engineers to abandon wood and canvas, right? And build the first stress-skin all-metal monoplanes?
The aerospace industry has never looked back since. Modern commercial aircraft are still constructed predominantly from advanced aluminum alloys. It survives the immense pressure cycles of high-altitude flight way better than early alternatives.
And beyond our atmosphere, right? Rockets, the International Space Station, the satellites routing our global communications, they all rely on aluminum's unparalleled strength-to-weight ratio just to keep launch costs viable.
But you know, the material's impact is just as profound on the ground. Think about the device you, our listener, are using right now. to listen to this deep dive.
Smartphones, laptops, tablets, they rely heavily on anodized aluminum casings.
Yeah, it provides structural rigidity for thin screens while acting as a massive, highly efficient heat sink to draw thermal energy away from the processors inside.
And we also have to look at the power grid itself. I was surprised by this one in the research.
Oh, the transmission lines.
Yeah, because while copper is a slightly better conductor of electricity, it's incredibly heavy and expensive.
Ah.
So those high voltage transmission lines, the massive cables moving power from plants to cities, they're made of aluminum wound around a steel core.
Exactly. The aluminum handles the electrical transmission, and its lightweight means we can space the transmission towers much further apart, saving billions in infrastructure.
And as we shift toward renewable infrastructure, the demand is only accelerating. The frames holding up millions of solar panels are extruded aluminum. They don't rust out in the rain, and they're light enough for residential roofs.
Plus, the automotive industry is rapidly replacing heavy steel components with high-strength aluminum frames to increase the battery range of electric vehicles.
All of this incredible utility, however, forces us to confront a severe environmental tension.
This raises an important question, doesn't it?
It does. We have to look at the energy paradox of element 13. We are heavily reliant on it to build a sustainable, fuel-efficient future, but the original extraction from ore, that Hall-Héroult electrolysis process, requires a staggering amount of electricity.
Yeah, breaking those oxygen bonds at an industrial scale is one of the most energy-intensive manufacturing processes on Earth. The industry has grappled with this carbon footprint for a century.
Are we creating an environmental disaster just to keep our laptops light?
Well, primary aluminum smelters require so much constant massive amperage that they are rarely built near the bauxite mines. Instead, the alumina powder is shipped halfway across the world to places like Iceland, Quebec, or the Pacific Northwest.
Specifically to be next to massive, dedicated hydroelectric dams. They need cheap, abundant, uninterrupted power.
Right. If a smelter relies on a grid powered by coal or natural gas, the carbon footprint of creating that virgin aluminum is just devastating.
But the research points out a profound saving grace for the life cycle of the metal, right?
Yes. It comes back to the atomic structure. Aluminum is 100% endlessly recyclable.
Because the atomic structure doesn't degrade, you can recycle the same piece of aluminum 1,000,000 times, and the 1,000,000th time, that crystal lattice will be exactly as strong and useful as the day it was ripped from the dirt.
Exactly. The atomic bonds don't suffer fatigue from being melted down. But the most vital metric here is the energy comparison. Recycling aluminum requires only about 5% of the energy it takes to produce new aluminum from ore.
Only 5%. That's a 95% reduction in energy use and greenhouse gas emissions.
And the physics behind that saving is really straightforward. When you recycle a soda can, you aren't fighting to break those stubborn oxygen bonds anymore. The Hall-Héroult process already did all the heavy lifting decades ago.
Oh, that makes total sense. All you have to do is reach its melting point, which is roughly 660 degrees Celsius, which is relatively low compared to steel.
Right. The economic and energy incentives are so perfectly aligned that the recycling system is just incredibly efficient. A recycled aluminum can be melted down, cast into a massive ingot, rolled into a thin sheet, stamped into a new can, filled, and placed back on a supermarket shelf in just about 60 days.
That's the absolute cornerstone of a circular economy. And the data suggests that nearly 75% of all the aluminum ever produced in human history is still in active use today.
It's a staggering reality. 3/4 of all this metal ever refined is just endlessly looping through our society, shifting from like an airplane wing to a car chassis to a window frame.
Which brings up the reality of our physical proximity to it. I mean, we are constantly surrounded by this metal. We touch it, drink out of it, cook on it. Looking at the health and safety data, how does the human body interact with element 13?
Well, the epidemiological data is very clear on consumer safety. For the average person, everyday exposure to aluminum is perfectly safe.
Okay, good to know.
Yeah. When we use aluminum in food packaging or pots and pans, that microscopic sapphire hard oxide layer we discussed earlier forms a nearly impenetrable barrier. It prevents the raw metal from leaching into your food or water in any meaningful quantities.
And our bodies can handle trace amounts anyway, right?
Exactly. The human digestive system is highly adept at filtering out the minuscule trace amounts we might ingest naturally from soil and water, safely eliminating it through the kidneys.
The workplace environment, however, requires a completely different level of respect.
Absolutely. The manufacturing side of aluminum involves significant occupational hazards. When aluminum is machined, ground, or cut, it produces a microscopically fine dust.
And if that's inhaled repeatedly over long periods,
That dust can accumulate in the lungs and cause severe respiratory issues, a condition known as aluminosis.
but beyond the respiratory risk, there is also an explosive danger. Right?
Yes, a massive one. Because aluminum is so highly reactive and eager to bond with oxygen, fine aluminum powder is incredibly combustible.
Wow. So if that dust is suspended in the air in a factory and finds a single spark,
The resulting oxidation reaction happens so rapidly that it causes massive, devastating explosions. Industrial facilities have to adhere to extreme ventilation, grounding, and housekeeping regulations to prevent any dust accumulation.
it demands rigorous safety protocols on the factory floor. But, once it is alloyed, cast, and finalized into a solid product, it stabilizes into one of the most reliable materials we have.
And looking ahead, high-performance manufacturing is only going to push this material further. Metallurgists are currently developing new aluminum-lithium alloys for the next generation of spacecraft.
Reducing weight even further while maintaining structural integrity. The trajectory is so clear here. Aluminum proves that abundance alone doesn't make a material useful human innovation does. I mean, it took centuries of chemical struggle and massive feats of electrical engineering to finally pry it from the dirt, but that effort ultimately unlocked the modern world.
Yeah, it transformed from an emperor's novelty into a material that supports global logistics, advanced computation, and the entire transition to renewable energy.
Lightweight, resilient, and endlessly capable of reincarnation. But I want to leave you with a final thought to consider today, something that takes the story of this metal even further into the future.
Oh.
Because aluminum is the primary material we use to build satellites, and because low Earth orbit is becoming increasingly crowded, older satellites are constantly being intentionally deorbited to burn up in the atmosphere.
Right, space debris management.
Exactly. Well, astrophysicists are now tracking a massive influx of vaporized aluminum accumulating in the Earth's upper atmosphere from these re-entering spacecraft.
Wait, really?
Yes, and they're actively studying whether this microscopic dust might eventually alter atmospheric chemistry or reflect sunlight in unpredictable ways.
Wow.
So the next time you look up, just remember, the exact same metal that allowed humanity to conquer the skies might eventually be the element that changes them.